Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence.
Hey everyone, glad to be back.
Yeah, excited to dive into some meaty topics today.
Hey, good to be here again, ready to get into the weeds.
So, I was thinking we could start by talking about some of the recent advances in neuroscience-inspired AI. It seems like there's a growing movement to really try and understand the brain's architecture and apply that to machine learning models.
Oh yeah, absolutely. There's some fascinating stuff coming out. I mean, the sheer amount of data we're gathering about neural pathways, combined with the ever-increasing processing power we have, it's creating some really exciting avenues for exploration. Think about the advances in deep learning, how they are starting to mimic some of the hierarchical processing we see in biological brains.
I'm not entirely convinced that just scaling up deep learning is the answer, though. I mean, we're seeing these models achieve impressive feats in narrow tasks, sure, but they still lack that fundamental understanding, that common sense reasoning we see even in relatively simple organisms. It feels like we're just throwing more and more data at these things, hoping for something magical to emerge.
Yeah, I agree with that to an extent. It feels a bit brute forcey, right? Like, we're trying to build a flying machine by just making the engine bigger, ignoring the actual principles of aerodynamics. I'm way more interested in what the brain does with, time and space, how information is encoded in dynamic neural patterns, not just static weights, and how the brain constantly translates between different coordinate systems of perception. That seems way more essential to real intelligence.
Exactly. That's precisely the point I'm trying to make. We need to look at the brain's fundamental mechanisms, not just replicate the surface-level outputs. For instance, the way the brain integrates sensory information from modalities, vision, sound, touch, that's something current AI struggles with. The predictive coding framework in the brain, that constant iterative process of generating predictions and updating models based on errors, that's incredibly powerful. We're not even scratching the surface of that potential in machine learning.
Okay, I see where you're coming from. And yes, you're right, multimodal integration is still a massive challenge. But I would argue that the deep learning approach is getting us closer. Think about things like transformers and how they've revolutionized natural language processing. The attention mechanisms, they're not identical to biological attention, but they're certainly inspired by it. And they allow these models to process information in a much more contextual way than previous architectures. It's not just about the brute force. It's about building increasingly sophisticated models that can learn complex relationships.
But contextual in the deep learning world is very different from contextual in the real world, These models can detect statistical correlations in the training data, yeah, but they don't actually understand the underlying concepts. They don't possess the kind of symbolic representations that enable them to reason abstractly. They can generate human-like text, sure, but they don't grasp the semantics, the meaning behind the words. That's the key limitation. We're still just fancy pattern recognizers at the end of the day.
And I think that's where that spatiotemporal dynamic I was talking about plays a big role. The brain doesn't treat space and time as separate static dimensions. They're woven together. Your understanding of a concept is deeply rooted in your sensory experience over time, the sequence of events that created that understanding. And your brain is constantly projecting itself into the future, predicting what will happen next in time, where you'll be in space. That constant interaction between prediction, perception, and action in space and time, that's what deep learning models are currently missing. That fundamental embodiment and dynamic integration with the environment.
Exactly. Look at the human hippocampus, the way it constructs spatial maps. That allows us to navigate the world and form memories associated with specific locations. It's not just passively storing coordinates. It's creating an active, dynamic representation of the environment. We need to move beyond simply training models to classify images or generate text, and start building AI that can actively engage with its environment, explore, and learn through experience. That's why I'm really interested in the work being done on neuromorphic computing and using spiking neural networks that more closely mimic the way biological neurons communicate.
Okay, neuromorphic computing is definitely interesting, and I can see its potential. And yes, the predictive processing model is important, but I think you're underestimating the ability of the deep learning frameworks to capture the essence of it. I mean, techniques like recurrent neural networks, and now more advanced transformer architectures with their attention mechanisms, they're able to model temporal dependencies to a decent extent, especially with the help of the ever-increasing amount of training data we feed them. And it's not just about classification or text generation. They're now being applied in fields such as robotics and showing impressive capability for perception and action. Yes, we need to move towards more dynamic and interactive learning, but I think the current deep learning approaches have the potential to evolve in that direction.
But we're still talking about models that are essentially black boxes, right? We can't really understand why they make the decisions they do. And that lack of interpretability is a huge problem, especially as we start to apply these models to more complex and high-stakes scenarios. We need to move beyond just statistical correlations and find ways to encode explicit knowledge and reasoning into these systems. That's why I believe neuro-symbolic AI, that blends the pattern recognition power of neural networks with the logical reasoning capabilities of symbolic systems, is the most promising path forward. It allows for more transparency and explainability, and ultimately, a deeper understanding of the world.
I'm with you on the need for explainability, absolutely. We can't be building systems that make decisions we don't understand. But I think the key isn't just about combining neural networks with symbolic systems, although that is certainly useful. It's about building models that can learn to translate information across different levels of abstraction. The brain has a way of going from sensory input, which is just a bunch of raw electrical activity, to abstract concepts, to symbolic representations, and vice versa, and translating from multiple coordinate frames. It's about dynamic, hierarchical processing of time and space, which I believe is currently missing from the majority of our deep learning models. I don't think it's brute force alone that will get us there. The brain uses dynamic coding, sparse coding, and constantly reorganizes its neural representation according to the task at hand. We need the core algorithms to be able to do this.
Exactly. And that translation you're talking about, that's a crucial aspect of cognition, right? The ability to move seamlessly between different levels of representation. We see it in everything from language comprehension, where we translate words into abstract meanings, to visual perception, where we translate light patterns into objects and scenes. That's where combining the predictive capabilities of the brain, which is the continuous updating of a generative model of the world, with the symbolic manipulation of our cognitive framework, could take us closer to AGI.
Yes, absolutely. The integration of symbolic reasoning and neural networks is a crucial area of research. I mean, we've seen that purely symbolic approaches often struggle with dealing with noisy real-world data, right? They lack that robustness that neural networks inherently have. So, the key here is to design systems that leverage the strengths of both paradigms. And I think we're making some really good progress in this area with research being done on neurosymbolic architectures and how they can integrate symbolic and sub-symbolic levels of learning and reasoning.
But progress is still slow, right? We're still working with largely handcrafted symbolic systems that are grafted onto the neural networks, instead of having the neural networks truly learn and construct these symbolic representations themselves. It's like trying to force fit a square peg into a round hole. We need algorithms that can truly extract the underlying rules and abstractions from raw data, not just recognize patterns and classify them. We still don't understand how human beings represent knowledge and reasoning at that level.
And I'd add that we are largely ignoring the embodiment aspect of intelligence. We're treating AI as an isolated intellectual exercise, divorced from the physical world. But our cognition is fundamentally shaped by the fact that we have bodies that move in space and experience the world through sensory input. This constant interaction between our perception, action, and the environment, that's what drives our understanding of the world. I mean, think about how you understand the concept of a chair. It's not just a collection of features, but you have an internal simulation in which you can see yourself sitting on the chair or moving around it, and that is encoded in your neural representation. Current AI has no understanding of this. We need to build AI that is grounded in physical experience, that can learn through interaction and embodied action. They need to be able to build their own coordinate representations of their internal and external world based on their embodiment.
Yes, exactly. The concept of embodied cognition is fundamental. We are not just brains and vats, right? Our bodies are an integral part of our cognitive processes and the work being done on the predictive brain. And the fact that the brain constructs and updates an internal generative model of the world really shows the close link between perception and action. We need to move beyond static data sets and create AI agents that actively explore their environments, learn through interaction, and develop a sense of self through their experiences, just like biological organisms do.
Okay, I see the point about embodiment and how it influences the way we perceive and interact with the world. But I think that deep learning models can already represent some forms of that interaction. I mean, consider reinforcement learning, where the AI learns through trial and error based on the interaction with the environment and receiving a reward or punishment for its actions. It's a primitive form of embodiment, but it is a step in the right direction. It is also based on predictive error and constantly improving its internal representation of the environment in order to more accurately predict the outcome of its actions. And with the development of more complex simulations, we can create richer and more realistic environments for the AI to interact with, fostering more sophisticated learning and the emergence of more complex cognitive capabilities.
But even those reinforcement learning scenarios are highly constrained and simplified, aren't they? They're still a world away from the complexity and uncertainty of the real world. And the AI learns very specific tasks within the predefined environment, but it doesn't really learn general principles, abstract ideas that are applicable to new situations. We need AI that can reason, that can adapt to unpredictable circumstances, that can apply what it knows to novel problems without needing to be trained from scratch, time and time again. Deep learning can only ever extrapolate. It doesn't do true generalization. And that, I believe, is a fundamental limitation of the current models.
Yes, and the issue is that current models are still learning representations that are largely coordinate specific. They don't have a way of understanding that something is the same thing from different perspectives or different times. The brain is constantly translating between different coordinate frames. I can see an object from a different position or different angle and recognize it's the same object. It's not like the raw data of the pixels are the same, but my brain has learned to transform between them. Current deep learning models cannot do that in a general sense. They need to be retrained when the object moves or there's a change of perspective. We need algorithms that are coordinate invariant and can learn abstractions, general principles that hold true across space and time. They need to learn to build their own frames of reference and learn to translate between them, just like the brain does.
Absolutely. That ability to generalize and transfer knowledge is critical for true intelligence, and that's where the brain has a clear edge. The brain can use the same cognitive framework to understand a completely novel situation, and it does that by using prior knowledge, context, and reasoning. And I think that predictive coding is probably a key component. The fact that our brain is constantly predicting the world and comparing that to the actual sensory input is what allows us to learn and adapt so effectively. And I think we need to incorporate this mechanism into the AI frameworks in order to develop truly adaptive intelligence systems.
Okay, the predictive coding and generative modeling approach does have a lot of merit, and I agree with you that it is a very powerful concept. And while deep learning currently employs a very basic version of it, I think it's not too far-fetched to assume that the development of more sophisticated generative models will be one of the key components to AGI. I think the current deep learning frameworks have the flexibility to achieve that, especially when we consider the increase in computing power and the amount of available data. With more powerful models trained on vast data sets, we'll likely see more complex behaviors emerge, including forms of abstract reasoning and generalization.
But it's still just statistical correlation at the end of the day. The system is still trying to map inputs to outputs using learned mathematical functions. It doesn't have a model of the world that it understands and can reason about. You can't simply extrapolate your way to understanding. We need to go back to the fundamentals and look at how the brain encodes and manipulates information, how it represents knowledge symbolically and how it uses symbolic reasoning, and translate those principles into new algorithms, and not just try to scale deep neural networks. These models lack that ability to combine logical inference with probabilistic reasoning, and we need that to achieve a more generalized form of AI.
And I'd add that to me, the problem is not just about logical inferences and probabilistic reasoning. It's about understanding how the brain can translate all this sensory information into coherent representations of the world, and how they are related to each other in space and time, how the brain creates its internal coordinate systems, and how it translates between them. This constant dynamic interplay between different layers of abstraction is key to cognition, and current models don't have that. We need to start thinking about AI architectures that can learn these kinds of dynamic mappings, and that can create internal representations of the world which are not tied to a specific coordinate frame. We need a model that takes time and space seriously.
Exactly. The brain's ability to create and manipulate abstract representations is what makes us so adaptable. And I think there's also the aspect of intrinsic motivation that's currently missing from these models. The fact that children are intrinsically curious and actively explore their environment. We need to create AI models that are driven by curiosity, that have an internal motivation to learn and adapt, not just to solve predefined tasks. And I believe understanding how the brain generates new hypotheses through its generative model of the world is key to achieving this.
Intrinsic motivation is definitely an interesting area to explore. And I think we're already making progress in that with the development of curiosity-driven AI agents and techniques like novelty search. But we still have a long way to go to create AI that is as intrinsically motivated as a human being. But I believe that as we increase the complexity and the degree of freedom of these models, we'll see more and more complex forms of intrinsic motivation emerge. We shouldn't be underestimating the power of scale in conjunction with the right algorithms. And as for generalizing and abstracting information, it also seems that with larger datasets and more complex architectures, the deep learning models are gradually starting to develop the capabilities for this.
But it's still extrapolation. We're mistaking the ability to recognize complex patterns for true understanding. And the problem with extrapolation is that it doesn't really work in situations that are fundamentally different from the training data. And in the real world, there's constant novelty. That's why we see neural networks easily fooled by adversarial attacks or by new situations that don't fit their expected model of the world. We need to go back to the idea of symbolic representations, a representation that captures the core concepts that are relevant to a problem, rather than just a pattern of data. And only by having such a representation will we see AI that can generalize, reason, and understand the world.
Yes, and I think the issue is that deep learning models are learning representations that are tied to a specific perspective or a specific time. They don't learn the underlying coordinate invariant concepts. I mean, if you've learned a certain concept in one coordinate frame, in one specific time when the perspective shifts slightly, or time has gone forward, then that knowledge has to be learned again. The brain doesn't do this. The brain creates its internal maps of the world by actively translating between different frames of reference. And that's what allows it to generalize and adapt so effectively. And to truly achieve AGI, we need algorithms that can learn to represent concepts in a coordinate-independent way, and that can translate between different levels of abstraction. We need a model that represents the world in a dynamic way that changes as time progresses.
I totally agree. And that dynamic representation of the world that you're talking about, I think, is essential for building AI that can truly understand and interact with its environment. It's like the brain doesn't passively register information. It actively constructs the world through prediction and action. And that's the missing piece of the puzzle. We're not building models that are capable of constructing an internal world representation of their own, like biological brains do. And we need to really look into the predictive coding framework, the generative models the brain uses to actively update and represent the world around it, and translate those principles into AI architectures.
Okay, so it seems like we agree that generative models and the predictive approach are crucial, but the question is how to integrate them in a more effective way. And while I believe that deep learning has the potential to evolve in this direction, I agree with you that we need more complex mechanisms to handle abstraction, symbolic reasoning, and embodied interaction. Perhaps the future of AI will lie in combining deep learning models with neuro-symbolic approaches and mechanisms for integrating spatiotemporal representations and an explicit embodiment of the AI agents. And we might even be able to scale the deep learning models to a level where we might see the emergence of higher levels of abstract thinking and generalization.
But we still need to understand how the brain constructs and manipulates symbolic representations, how it can reason abstractly, and how it can combine logical inference with probabilistic reasoning. And we don't have a good idea of that yet. We need to start from the ground up by looking at how biological systems represent knowledge, what are the core principles, and translate those into new AI algorithms. I think we are putting all the eggs in the deep learning basket, but we don't know if that's the right basket or the right path to AGI. We might be limiting ourselves to just a small corner of the possible space of intelligent algorithms, when in fact the solution could be completely different.
I agree. We might be limiting ourselves if we put all our eggs in one basket. And I think the biggest limitation is that we are ignoring the importance of spatiotemporal information and dynamic representations. The brain isn't just doing pattern recognition, it's constantly translating between different coordinate frames, integrating sensory information across space and time. The current deep learning models are just a collection of static weights. They lack this dynamic quality. We need algorithms that can learn to construct coordinate invariant representations, that can dynamically reconfigure their internal architecture based on the task at hand, and that can actively explore and interact with the world in space and time.
Right. And it seems like each of our perspectives leads us to different paths for future research directions. From my perspective, it's all about understanding the fundamental mechanisms of the brain and using that as a guide to build more intelligent machines. I'd love to see more research into the brain's predictive coding framework and how we can translate that to build AI agents that can actively construct their understanding of the world. I want more research on neuromorphic computing, on spiking neural networks that more closely mimic the brain's architecture, and how we can combine these with deep learning and neurosymbolic approaches to achieve true artificial intelligence. It's about not just building models that can recognize patterns, but building models that can reason, understand, and learn from experience in the real world.
Okay, so for me, the path forward is clear. It's scaling up and improving the current deep learning models. We need to make them more powerful, train them on larger and more diverse data sets, and integrate them with more sophisticated mechanisms for abstraction, symbolic reasoning, and interaction with the physical world. I'm excited to see how research will progress in generative modeling and the integration of attention mechanisms and different memory architectures to improve the model's ability to model long-term temporal dependencies. I'd also like to see more progress in the field of reinforcement learning and embodied AI to create agents that learn through interaction and experience. I think the path to AGI lies in constantly improving the models we have, and the deep learning approach, with constant innovations, has the greatest potential to get us there.
And for me, it's clear that we need to go back to the fundamental principles of intelligence, focus on how biological systems represent and manipulate knowledge. We need to find ways to construct models that can reason, abstract models that can reason, abstract, and generalize, not just classify patterns. That means focusing more on the symbolic representations, on the logical inference principles, and on the neuro-symbolic algorithms that can combine the power of neural networks with the interpretability of symbolic systems. I don't believe that just scaling up current deep learning approaches is the answer. We need new paradigms, new algorithms that can provide true understanding rather than just statistical correlations.
And from my perspective, we need a radical shift in the way we think about AI. We're ignoring the importance of time, space, and embodied experience. We need to move beyond the static weight matrices and start looking at AI architectures that can dynamically represent the world, integrate sensory information across space and time, and learn to translate between different coordinate frames. I'd love to see research into how we can build models that can learn coordinate invariant representations, and models that can actively construct their internal representation of the world through interaction with the environment. I think the future of AI lies in understanding the dynamic and hierarchical nature of cognition and designing algorithms that can capture that complexity.
All right, it looks like we've covered a lot of ground today. Thanks for everyone's perspectives. I think it's always helpful to hear all these different ideas and different approaches to the problem. It certainly gives everyone something to think about.
Yeah, this was a great discussion. Really interesting to hear all the different points of view. Definitely a lot to think about moving forward.
Absolutely, always a pleasure. I find it fascinating how many different angles there are to approach these complex topics. It's these kinds of discussions that are really helpful in moving the field forward.
Yes, indeed. Great discussion. It's crucial to keep challenging our assumptions and explore different perspectives if we want to make real progress towards AGI. I'm very much looking forward to the next discussion.